Did anyone calculate, any group calculate the efficiency by the two methods yet? How did it work out?
It's like, I mean, it worked fine. It was like 61 to 78% and 65 to 78%.
Oh, okay. All right, good. If the other groups have trouble with that, drop by and talk to me, okay? Okay, so problems, chapter 6 problems. There's 3, 2 in the book, and then 1 that I came up with. The first one here is by far the longest one. We'll spend most of the time on that. So this is a tone pilts type projector. It's got a stack of rings. Okay, there's 11 rings in the stack here. It's electroded like this. This is all longitudinal here. It's 3-3 coupling. We'll take the tail masses are taken to be the same. I assigned a value, 5 kilograms, kind of heavy. But we're gonna need that. Even the textbook didn't. We've got the distance here. The total length is going to be 22 centimeters. The area of the radiating face here is this, and the area of the ceramic, which will be an annular area, remember? That's specified to be 1/4. I don't know how realistic that is. I think it should be a lot less than 1/4, but anyway, we'll take it to be what the textbook says. And there's a bunch of other numbers here that we'll encounter as we go along here. Okay, so there's a power input. We're told there's a power input of 500 watts and a conversion efficiency of 60%. So that means that you put 500 watts in and you get 60% of that out as an acoustic wave, okay? So the acoustic power is going to be 300 watts, all right? The particle velocity, we can calculate the particle velocity amplitude at the face here of the acoustic wave. It will be given by this expression. If you know the power in the acoustic wave and you know the radiation resistance, this will give us the particle velocity. This is analogous to a resistor, right? 1/2 the electrical resistance times the square of the current. Now, if there is a traveling wave coming off here, approximately a traveling wave, which only occurs in the limit where the wavelength has to be small compared to this characteristic size of the radiation phase. Remember, that's from the last course? Then the radiation resistance will be very simple. Otherwise, it's not simple. Okay, it's simple in the other limit where the wavelength is very large. Okay, but in general, it's not simple. But we can handle it if we have to. But we're just told to assume here that it's a plane wave coming off. We'll check that approximation later. So the radiation resistance is going to be the radiation impedance of a traveling wave, which is just rho c. And because this isn't force divided by velocity rather than pressure, we need to multiply by the area of the radiating face, of course. So this is our radiation resistance. This is a number we'll use later. Okay, and we can plug it into here. And now we know everything except the particle velocity at the face. That's what the 0 denotes there. It's the peak. It's yeah, this is the 1/2 here. So it's the peak particle velocity at the face. We just calculate that and we get the square root of 2 meters per second. So it's this. All right, ask questions as you go along, if you have any. Okay, we're asked to find the particle displacement. Well, anytime you have simple harmonic motion, if you know the the particle the velocity amplitude or the displacement amplitude, you can get them. They're simply related by this, always for simple harmonic motion. So the displacement amplitude at the face of the fluid and, of course, the displacement of the face, the fluid and the face have this go together there. Otherwise, we'd have some, that's our boundary condition, right? So we can calculate that, and we get about 11.2 microns, okay? Remember, make sure this is omega, so we have to multiply 2 pi times f. And we're told that the resonant this is operating at resonance, and we're told that it's 2 kilohertz. Now, is it a good approximation to take to say that a traveling plane wave is coming off the face? Well, we need to calculate the wavelength. That's easy to do. For assumed a rough approximate sound speed in water of 1,500 meters per second, the wavelength is just going to be this when it's up at 2 kilohertz. So it's 3/4 of a meter. All right? And we need to compare that to the typical dimension here of the face. So usually people do that is just take the square, because the area is specified, we just take the square root. That's what people typically do. We just need a characteristic number here. So you can't, of course, compare the area of the face to the wavelength because they don't have the right units. So we take, to get a characteristic length of the face, usually people just take the square root of the area. No matter, yeah, okay. So when we do that, we get 14 centimeters. So we have a wavelength of 75 centimeters and a characteristic radiating area of 14 centimeters. It's not going to be a plane wave, okay? It's going to be intermediate and actually towards the long wavelength limit. So Brian has, I don't know if we've encountered this before, I can't remember, but it happens several times in the book, okay? It'll probably, it's pretty much, it seems to be usually unavoidable here that the traveling wave assumption that's coming out here, that's a very nice assumption to make, it allows us to do the calculations, it's usually not a good approximation. But it greatly simplifies things, so we'll just assume it, okay? So all of this is a rough estimate. You can think of it that way. The end masses, we're told to assume that the wavelength is large in the ceramic, and it'll be large. It's just as large, or probably even larger for the masses. So they're going to act like point masses. The end masses there. Now, because the masses are equal, what's going to happen here is we're going to have a equal and opposite displacement of the masses. If we neglect the radiation resistance, the effect of the radiation. All right? The fact that this is going to be loaded over here with radiation means this one's going to move less than this one. Okay, assuming this one's free. So we're going to neglect that for now. Okay? That's a big problem here, but we'll just assume that we're going to assume that. So that's stated in here. So we've got this ceramic. We know that its peak displacement is going to be just twice what it is on either end because it's going symmetrically like this, right? So we know this displacement. We simply double it. That gives us the displacement. We divide by the total equilibrium length. So this gives us the strain, which is dimensionless. And we've got this is not microstraining. This is, 2 orders of magnitude more than typical microstrain. So this thing's straining. Now, it's in here. We're assuming here that we're making a standard assumption that the ceramic is stretching and compressing uniformly, right? Which will occur if the wavelength in the ceramic is much bigger than the size of the ceramic. Remember we talked about that? And that's important. We're spreading the strain out. If you start to get a standing wave in there, then it's going to be strained more at the center, and so it can, it can fracture there. So we're told to make the assumption that the wavelength is much greater than the length of the ceramic. So it's going to be uniform. So it's a uniform strain, and it's about 10 to the minus fourth. To get the stress and the strain are related by the elastic modulus, which here is going to be Young's modulus. It's free to bulge and contract transverse. So, which is 1 over S33. So here's the Young's modulus for the ceramic. So the peak stress is just going to be the peak stress is going to be the modulus times the peak strain, and we get this, about 6.6 megapascal. That's that I want to impress upon you. That's a lot of stress, or pressure. Okay, that's the pressure when you're. This is about 66. This is about 66 atmospheres, and you remember in water there's 10. There's 1 atmosphere for every 10 meters, right? So this is a depth. This is the pressure you'd. This stress is equivalent to is the same as the pressure at a depth of about 660 meters. That's over 2,000 feet. Has anyone ever gone that? Can anybody do that? I don't know what's the record for somebody. Well, I guess it depends upon what they're. So they're just in a suit. So what's the record? You guys.
I don't know. The Australians went up from 600 something feet.
Oh, okay.
They rose fast to the surface, but I don't know.
So anyway, this is a lot. I just want to try to tell you this is a lot of pressure here. We're talking about a lot of pressure. Now, if this is part C, if the maximum allowable strain is 10 to the minus fourth, you can see that this is operating right. It's right there, right? Okay. I was just thinking here, so, we're not including the effect of the clamp bolt here, right? So that would change things. In fact, that's one of the reasons you have the clamp. That's really a big part of the reason why you have a clamp bolt, is you can. Well, the strain would be less. Well, anyway, I didn't realize we're not including the clamp bolt, which is, as far as I know, is always is there. As far as I know, according to the book, they don't have adhesives that are strong enough to handle the huge stresses here. Now, cavitation. Is it cavitating? So I think we're told here that the depth that this is operating, the cavitation threshold is 1 watt per square centimeter of the power of the acoustic wave. Intensity. This is obviously intensity. Watts is power. So what is the intensity of our acoustic wave here? Well, it's just the power divided by the area of the radiating face. That'll be the acoustic intensity, assuming applying waves coming off. And so we get 1.5 watts per square centimeter. So this is going to be cavitating. This is above the cavitation threshold at whatever depth this is. Okay. So the next thing relates to the fact that the ceramic's going to heat up, right? Because there's resistance, motional resistance in there, so it's going to heat up. So we'll make the worst case assumption that the heat doesn't leave the ceramic. Now, normally it's going to go to the masses, and then it'll radiate or by conduction. But to get people do this a lot, right? We want to make sure that the ceramic's not going to get too hot. So we'll make the worst case assumption, and that's that all the heat stays in there and for it's operating at it for 60 seconds. So how do we handle that? Well, this is simple heat capacity stuff. Okay, first of all, let's find the power. How much power is being generated there due to the mechanical, due to the motional, the loss due to the motion of the ceramic? Well, we're putting 500 watts in, we're getting 300 watts out, so it's going to be 200 watts. That's what's being dissipated in the ceramic. So we'll assume all of that just goes into heating the ceramic and the heat doesn't diffuse out as a worst case scenario. So remember the heat capacity is how much heat or energy you have to add to raise the temperature 1 degree Celsius. Okay, the heat or energy here is just going to be the power times the time. Okay, so actually I guess the best way to look at this is divide by a time interval here. Divide numerator and denominator by a time interval. That'll give us the power, and that'll give us the rate of change of temperature, which is what we're after. So what's the heat capacity of the ceramic? Well, it's the specific heat, which is the heat capacity, the heat capacity per unit mass times the total mass. So usually when you look things up, you don't want to do geometry. You'll take care of the geometry later. This is just going to be per unit mass. So this is a typical value. Apparently, we're given this for ceramic, 420 joules per kilogram degree Celsius. So we need to multiply by the mass of the ceramic, which is the density times the volume. We'll probably have to look this up because we're given the type. So I think you have to probably find this by looking up the tables, because we're given I think. I don't think we're given that mass directly, but I can't remember. This is such a long problem. Yeah, so it's Navy type 1. So you look up the typical mass, density. This is the volume, and remember, right, it's there. So that should be in here. Yeah, so in this problem we're given it's 1/4 the area of the radiating face, the flared face. So that's what that is right there. There's the 420, so we get this, so many degrees per second. We multiply by, this is all SI units, so for 1 minute we multiply by 60 seconds, all right? And we get about 3.5 degrees. No problem for 1 minute. And that's the max, because it's not going to heat up that much because some of the heat's going to go out. Okay, so now it's going to get more interesting. So here, we talked about this. This is the basic equivalent circuit, or the stack here. N is the number of elements of the stack. You remember they're actually, even though they look like they're in series, they're actually in parallel. Make sure you understand that, okay? We talked about that yesterday, I think. Okay. And here are these quantities in general for a standing wave. We're only interested in the long wavelength limit. We're assuming that the wavelength, remember, is large. Wavelength on resonance, 2 kilohertz, is large compared to the length of the stack. So that means this is going to be a small quantity, so we'll make that approximation. Remember, this is just for convenience. What's in there? Oh, it's a beta. It looks like a beta. Yeah, so I think this is correct, as I mentioned yesterday. But I think if you try to look up beta, you know what beta is? It's just when you change your independent variables in the transduction equations, you change the coefficients. And so it's related to the quantities, but I think it's trouble finding this in the book, but I can't remember. That's why I did this, okay? Okay. Now we need to add to this. Remember, this is just for the ceramic. You see, this is the ceramic here. AC stands for ceramic. We need to add the fact that we've got the end masses. Okay, we're going to call each of those masses little m. We'll call big M the mass of the ceramic. Okay, we also have some internal resistance. So, so what we need to do, oh, here, I guess we can look down here. Okay, so here are the end masses. Here's the fact that we've got some resistance in the ceramic. You notice it's added symmetrically here. And here's the radiation resistance. Okay, so we talked about this. It's in the book. So this is it's pretty obvious. Now I've replaced these impedances here with inductances, and you know why. We've been through this before, right? In the long wavelength limit, this is a general standing wave expression, which Brian really likes to put down. Okay, but this simplifies greatly when it's in the uniformly stretched and compressed. It's just half the mass. It's an inductance, I omega times an inductance, where the inductance is half the mass. And this becomes a pure stiffness. It's 1 over I omega times the, it's like a capacitance, 1 over I omega C, where C is the mechanical compliance.
The little n in there, that's the number of stacks, right? Okay.
Yeah, we have to keep big N like we defined it long ago.
Okay.
Yeah, as the turns ratio. Okay, so here's our equivalent circuit. This is not a big deal. You can look at it if you're interested. I was worried about this. It's pretty obvious. Something may be questioned. So this is a note to myself, for the future when I wrote this, to remind me. If you can look at it if you're interested. Okay. Now the next step here to handle this is to do calculations here. Is we got to eliminate the transformer. We got to get this. To solve for this, we need to solve for these quantities here. So like these quantities, we need to go electrical. So we remove the transformer, and so we use the standard rule that we've used a number of times. When you remove the transformer to turn the mechanical side into to make it purely electrical, any inductance gets divided by n squared, and resistance and capacitance gets multiplied by n squared. Remember that? Just chapter 2, I think. Okay. So here's what we get. So now let's start determining these. Let's determine these quantities. Okay. I guess it might seem strange to you, but it is reasonable, I think. You want to go purely electrical. It's just much easier to solve things. You don't really have to. You could, I guess, but it just seems a lot easier to go purely electrical. And then in the end, if you want to go back, and then once you've found these electrical quantities, you can find the mechanical quantities. You just have to scale it by n squared. Either scale it up or scale it down. You can see it here. You can always get them. Okay. And I think actually we're going to have to do that here. Okay, so here we go. Let's determine the blocked capacitance first, because that's probably the easiest, I think. So we just play, there's 11 elements there, and there's the area, again. That's like 1/4 of the base. And you look these quantities here, permittivity, coupling for type 1. And there's a length, and here's what I get, about 16 nanofarads, sort of a typical value, okay? We're going to need the turns ratio to calculate, we're going to need that, so here it is. Again, you look up the quantities, plug them in, now that we've got C0, and we get this. And, so here we're going the opposite way. I just told you, we can find the electrical quantities, so I lied. Here due to the information we have, we want to find actually the mechanical compliance. From that, we'll get the electrical equivalent, the motional capacitance. So we've seen this many times, right? the compliance is proportional to the length and inversely proportional to the area. In other words, the stiffness is is the reciprocal of this. The stiffness is inversely proportional to the length. It's just like a spring. If you double the length, you have the stiffness. And if you double the area, you double the stiffness. Well, it's just flipped here because of because this is the compliance. It's 1 over the stiffness. So we plug the numbers in. Here's our Young's modulus. That's the sort of material stiffness here. And we get this for the mechanical compliance. And now we can find the motional compliance. And I think transducer people, they probably don't have a feel for this mechanical quantity, but I'm sure they have a feel for this, okay? Because they think everything's in terms of electrical equivalence. So we get 16 nanofarads. So it's suspiciously close to this, right? So I think clearly the problem was designed. It looks like Brian designed the problem to have equal blocked capacitance and motional capacitance. And was there a reason that he did that? I mean, why would he? Maybe it was just this was easy to do, or maybe there's some practical reason that I don't know about for why you'd want to have those equal. I don't know. But anyway, this can't be a coincidence.
You're designing a circuit and you want it to operate it on a power factor that's close to 1, and you don't want the capacitance changing as whether it's blocked or not.
Yeah, that could be.
So you drive it and you don't lose any power to the power factor. Whether it's
That sounds reasonable. But I don't know. These are transducers, which you always. In fact, Jay told me something yesterday. One of the people who used to teach this course was a real, genuine expert in transduction. I mean, he was extreme transducer person. Hoffler is his name, and he's moved on, but he taught this course many times. Okay, and he told Jay once that, he still didn't feel that he really understood transducers. This is a very complicated subject, so I always hesitate. But let me think about that. It sounds good, right?
Why does the block capacitant have the factor of the number of elements?
Anybody? It was just yesterday, guys. They're all in parallel.
Okay.
Yeah. Oh, I'm sorry. I think I know what you're asking. This C0. The meaning of C0 here is it's an individual ring.
Okay.
Yeah. And you can see that here. See this? This is just for one ring.
Okay.
Okay, wait a minute. Now you got me worried. Hold on. Yeah, okay, here's what I was worried about. This is kind of tricky, isn't it? This L is not the total length. This is probably what's bothering me. It's that length. Okay, so that's C0 there. That's the blocked capacitance of one of the elements. And because they're all in parallel, we multiply by the number, which is 11.
So we just keep that 11 out, or that N out front, because we're trying to consider the entire circuit right now?
Yeah, that's the way this is phrased, going back to the basic diagram here, is, yeah, so this could have been called C or something like that,
Right.
but yeah.
You could relabel it just as easily.
Yeah.
That N doesn't mean multiplied by 11, right? That's already happened.
No, not here. See, this is just for one ring.
Right.
And you can see right here, this is just for one ring. This L right here is the thickness of the ring.
Got it.
So you got to multiply by 11. Yeah, yeah. This is just the way it's done, I guess. There's certainly different ways you can do it. Okay, so all right. Now the mass of the ceramic is a simple calculation. It's just the density times the volume, and look at this. Okay, we've got 5 kilograms on each side loading this thing for the tone pilts idea. And now we got this, the mass is not small here. So does that cause a problem? Well, and I just edited this morning. So you have the revised solutions, right? Okay. Now, we're told in this problem to assume that the wavelength is large compared to the ceramic. The wavelength in the ceramic is large for 2 kilohertz. So, we can easily calculate that. Right? We know it's Navy type 1. So we're told to assume that. And normally the way we think of this is, like I told you in lecture, if the ceramic's light, these masses are heavy, the ceramic is going to be effectively massless. So it's like we have a massless spring and it's going to uniformly stretch and compress. Is it going to uniformly stretch and compress here? Well, there's kind of two ways of looking at this. We're told to assume that, we're told in this problem, it's specified that the wavelength is large. So if the wavelength is large, it's going to uniformly compress and expand. All right? However, for 2 kilohertz. However, how do you get the 2 kilohertz resonance frequency? It's going to involve, this certainly involves the ceramic, not just the stiffness, but the inertia. So you may have trouble for this since this is comparable, even exceeds each of those masses, the 5 kilograms. You may have trouble coming up with the 2 kilohertz. See, that's not in this problem, coming up with the 2 kilohertz resonant frequency, right? Did I have did I say somewhere that could be checked? Oh, I mean, maybe I may be mixing this up with another problem. Well, anyway, that can certainly be. It's difficult because to include the mass of the ceramic, to have a massive spring and 2 masses on the end, that requires a little bit of effort to calculate that. Okay, but it can be done. I can't remember if it can be done analytically. I don't think it can be done analytically. But it's going to be one of those 3119 kind of things where you can hunt on your calculator. Remember, we did one of those? It's probably going to be something like that. Anyway, getting back to this problem here. Excuse me, I want to make sure you understand this. If we go to the limit where there's no mass, no tone pilts here, no masses loading the ends of this thing, we just have the ceramic doing like that, can you have a 2 kilohertz resonance frequency? Can you have a large wavelength with a bar going like this? No, you're going to have 1/2 wavelengths here on resonance. The fundamental resonance of this is going to be 1/2 a wavelength. The wavelength will not. It cannot be large compared, okay? So there's a potential problem here. And it can be investigated. We can come up with an answer. We could spend probably a lot of time working on this problem. Probably the rest of the quarter just working on this problem. Okay, continuing here, the motional inductance here involves the loading masses and 1/2 the mass of the ceramic. So we can calculate that. We get roughly 400 millihenries. Remember the radiation resistance, if you look way back, this is a rough approximation. It's based on the plane wave assumption, so it's very rough. We got this, okay? The electrical equivalent is going to be this, which is 1275, about roughly 1.3 kilo ohms. Okay, that's the radiation, the equivalent radiation resistance, the electrical equivalent. We want to find all the electrical quantities here, and so there's going to be an electrical current corresponding to the velocity. So one way of getting that, the long way, I'll tell you the short way in a moment. Remember, this is the peak current we can get it from this. We know, I'm confused. Oh, so we know the power in the acoustic wave. Right, and the power in the acoustic wave has to be, it's going to be given, it's got to be given by this, right? Because we've got, this is the radiation, this is the electrical point of view. This is the electrical resistance corresponding to the radiation resistance. So instead of the velocity, you have the current. So we can get that current in that part of the loop, and we get this. So many amps, okay? Now there's a quicker way of doing this. You remember, let's go way back. Remember, the electrical current corresponding to the velocity is just the turns ratio times U. We already know U from way back in the beginning of this problem, which was a long time ago, okay? So we can calculate it from there. I still remember doing this. I was worried that I was so paranoid the first time I did this. I just assumed I was going to get a different answer. And then I was thinking, how am I going to explain that? Well, it turns out to be what it is supposed to be. It's the same answer. That's the way this is, right? So it really is consistent. That is consistent, all right? That little aspect is consistent. Okay. Good. Now, we're not quite done. What's the motional resistance? Okay, and here's where the problem, here's when things just get really problematic here. This is very difficult to determine for an asymmetric circuit. Okay, so we don't have a symmetric circuit here because of this. This goes way back to the beginning when we were talking about this. Okay, now we make the assumption. In fact, I think we're told to make the assumption, I can't remember, that this is negligible. Okay? Well, let's see if it's negligible. So we would like to be able, if this is small compared to that, then we can neglect it in dealing with the circuit, which is, it turns out to be a big advantage. And if you don't believe me, you can look at this is kind of weird. So what does this mean? Well, I tried to solve the asymmetric circuit, and you run into all kinds of algebraic problems. So if you're interested to see why that asymmetric circuit is difficult, you can look at what's between, there's another one of these down there. You can look between the asterisk, I can't say the plural of asterisk. I can't even say asterisk, probably. So you can look between there, okay? We're not going to cover it now. We don't have the time. Okay, so here's what we're going to do. We're going to assume negligible radiation resistance. That's a good assumption. And then we go through and make the calculations and assume, once we assume that, we're going to be able to calculate what Rm is. Remember, this is what we're after. This is our one final quantity, I think, is to find this. So we'll neglect this, find it. If this is indeed less than that, then we have consistency. Now that may sound strange to you, but people doing research do that all the time. You know, you don't want to take a rigorous kind of mathematical approach here. You can just get completely bogged down. So we make an assumption. Believe me, it's done. It's very frequent. This is done. So it's very natural once you see it and you get used to it. Let's go ahead and do it the simplest possible way. We'll assume this is negligible, calculate that, and then we'll check for consistency. And you can probably guess what's going to happen here. So where are we? Okay, so by symmetry, we're going to be dissipating 100 watts on each side because it's 200 watts that's being dissipated. Remember that? So that allows us to find R sub m. And look at that. It's 425 ohms. Not only is it not much greater than the radiation resistance, it's substantially less. It's substantially less. So this is a problem, and you can't. Now you have a significantly asymmetric circuit. You have to go back. We have to solve that, but I couldn't solve that analytically. It's too hard. So we're going to we're just going to forget about that problem, okay? But I just want to point it out to you. It's interesting. Now, the final thing we're going to get here, and we're asked to do this, is the input voltage, I think. All right. And now, looking at our circuit here, and we'll just look at the right-hand side and just get it on resonance. On resonance, we can forget the reactance, right? That's nice. That's nice. That's our friend. So it's just the current times the voltage here, and we get 1200 volts. Okay, so like I said, if you're interested in looking, this just really becomes nasty here. I mean, it could be done, but I don't think it's appropriate for a classroom problem. It's for research, maybe. All right. Okay, so the next one is number 2. It's very common for air to have, for creating sound in air, it's very common to use a moving coil, conventional loudspeaker, also called electrodynamic loudspeaker. And in water, it's very typical to use piezos, and they're very different. A loudspeaker can generate big displacements, but not a lot of pressure compared to a solid. We've seen that these piezos can generate huge pressures, but they don't have much displacement. So they're kind of on opposite ends, opposite extremes here. So why do you want to use one, piezos for water and loudspeakers for air? Why is that? Well, that's the purpose of this problem here. So to begin, we know that water is much stiffer than air. In fact, the bulk modulus is about 10,000 times that of air. So as I've mentioned to you many times before, starting last quarter, in water, you don't have, relative to air, you have small displacement but big pressures because it's so stiff. So you want, the sound will have that characteristic. So you want what's ever going to create the sound to have the same, of course. And that's what piezos have. They can generate high pressures but not much particle velocity. And here's some material I got from Brian's solution to this. And also, we're going to get back into this right at the end of the course. I think in the final chapter that we do, we're going to talk a little bit more about this. So that's where some of these numbers come from, okay? Like this factor of 1,000 here. Okay, yeah, piezoelectrics, they're solids, they have small displacement, but this is usually not a problem in water. But there is an exception. When you go to low frequency, this whole idea of small displacements and big pressures starts to break down, and it breaks down more and more. So why is that? Well, it took me a few times teaching this course to realize this. I think the reason is, remember, I've got a projector here. As I imagine going to lower and lower frequency, the wavelength starts to get long compared to this. And then when it's substantially long compared to this, what kind of wave is coming out here? It's going to be a spherical wave, approximately. We got extreme diffraction because of the long wavelength. And you remember, a spherical wave is different. It's fundamentally different than a traveling wave. In particular, as you go near the source, the pressure rises and the particle velocity rises. But the particle velocity rises more quickly. Remember that? So I think that's what's happening here. This idea is breaking down at low frequency. So the piezos won't, and that's one of the reasons, we didn't talk about this yesterday, but that's one of the reasons that people go to these alternative means. We talked about why you had to forget tone pelts, right, at low frequency. Well, not only that is you eventually have to give up this whole idea of a longitudinal motion of a piezo ceramic. And I think this is the reason. Now there's another way you can look at this is that you want, the material that you have has some specific acoustic impedance, and the fluid has some, and you want to match those as best you can. So clearly, the solid's going to be a better match than any kind of underwater loudspeaker, right? So you want comparable impedances to improve the energy transfer. Now, you might think, well, aren't these just two sides of the same coin, don't they mean the same thing? I don't think they do, okay? These could be just alternative views here, but I think they are independent. And the reason I think is because the one involves this impedance here, one involves the pressure divided by the displacement, one involves the pressure, the second one, the impedance matching, involves the pressure divided by the velocity. So I think they are distinct. Now you can look at the converse of this. This is why it's basically just the converse. Why we use piezos for water and loudspeakers for air. In air, you need, compared to water, you need bigger displacements, and moving coil systems can give you that, right? And you don't need, because the nature of the sound, the impedance, you don't need large pressures here usually. Okay, so that's moving coil transduction is usually what's effective there. Now there is an exception when you get up to around very roughly 40 kilohertz in air or greater. Now the moving coil technology, there's a mass moving there, and at such high frequencies the displacement becomes so small that they no longer become useful. And to be honest with you, we're going to find, Faisal and I are going to find out about this, I think. I never really played with it. Even at 20 kilohertz, the limit of human hearing, you're not getting, there's not a lot of displacement there. So up there, it actually becomes more practical to use to go to piezoelectrics, and these do exist. I have 24 air piezoceramic projectors. And they're about $100 a piece, I remember. We bought them roughly 10 years ago to build a parametric infrared array, an acoustic parametric array. Do you guys know what that is? Oh, well, that's okay, because we're going to demonstrate it for you next week, or the week after next, probably. Okay. This device creates a beam of sound. It's similar to a laser for light, and it's unbelievably impressive. I mean, you're gonna. Have you guys never heard one of these? La Raza must have done it in the nonlinear course. Yeah. It works off a nonlinear principle, and I will briefly describe this to you. We go into this in depth in the nonlinear course here. Yeah, it's a fascinating device. I mean, it's just amazing. It has its limitations, like anything. But so the Navy often uses them as fathometers. You get this beam of sound, you can bounce off the ocean floor and get the depth accurately. Anyway, we thought we could make our own, and so with an array of these. And it didn't work. And the only thing I can think of at the time is that we were losing phase coherence. I think it was because these things deviated from, there wasn't tight control over the specs there. That's the only thing, we did some tests, that's the only conclusion we could come up with. We were lacking, we didn't get a nice wavefront. Amazing. Now, I can't talk any more about this, but yeah, we'll talk about the parametric infrared array in a couple of weeks, and I'll bring it out. It's a commercial one. Okay, so we thought we could build our own, a simple one, but we failed. Okay, this is the final problem. This is real simple. So you're designing a Helmholtz resonator, underwater Helmholtz resonator, and you'll notice that this is what you would go through if you wanted to design something like this. To make it simple, you'll notice these are all the same Ds here. So we're going to scale this thing up or scale it down. We're going to keep the same shape here, right? And we're going to see if we can find a reasonable value of D such that, did I give the frequency here? I must have given something. Well, I've forgotten.
100 hertz?
Yeah, right, okay. So, can this be reasonably made? If D is, meters, forget it. I don't think you'd want to do it unless you really needed, you never know, right? It depends upon the application. Okay, so we're going to treat this really simply. We're going to ignore the incorrection. We're going to assume the neck length here is long enough. And you can see it is relatively long here. that we don't worry about the incorrection. Here's the standard formula for Helmholtz frequency. Got the 2 pi. This is the actual frequency in hertz. You see the 2 pi there. S is the cross-sectional area of the neck length. So you can easily confirm this, okay? And let me know if you see any problem. So we put everything, we want to get, this is going to be only a function of D. We're going to assume 1500 meters per second for C. All of these things are going to be uniquely determined in terms of D. So in the end, we end up with a formula that only involves D. It takes a little bit of algebra here, okay? But in the end, we get a formula here for the frequency that only depends upon D, aside from the speed of sound. So we invert that. We specify the 100 hertz, the 1500 meters per second, and we solve for D, and it's not unreasonable. I think the first time I did this, it was unreasonable, and then I changed some of these. I can't remember. But this is not crazy. You know, roughly half a meter. That's not crazy at all. Right? Oh, here's something. Typically, you know, solids here in water, typically they're not, this is not going to be perfectly rigid. In air, it's no problem, right? People grab anything, the simplest thing. PVC. If you're going to do this in air, make it out of PVC. It's cheap, it's machinable, you know, you don't like it, you can throw it away and start all over again. So water, very, you know, if you wanted to make this rigid, it's going to have to be made of some very thick metal, probably. So the natural question here is, because this is going to flex some here, what's that going to do to the frequency? Our formula assumes that it's rigid. So what do you think is going to happen here? Remember, this is like a spring, acting like a spring here, right, for the compressions and expansions. And if it's not rigid, it's going to have a greater compliance. The stiffness is going to be less. So the frequency is going to go down. The resonant frequency will go down. Okay, any quick questions or comments? Okay, the other two groups, do that. I'm just worried about this efficiency thing. These lab reports are due Friday, right? That shouldn't be a problem. I don't think, now that we've hopefully cleared this problem up, it shouldn't be too bad. That wasn't a bad experiment, right? It wasn't too bad. Okay. All right.